Hello, this is the last lesson of our exponential functions unit, and this is the applications involving exponential functions. So we're going to take a look at exponential growth and exponential decay. During the last lesson, we took a quick look at what these are, and we figured out that exponential growth must have a base greater than 1. And to find the base, you're going to add the rate plus 1. So 1 plus the rate. And by rate, I mean if it says 18%, you are adding 0.18 to 1. Okay, exponential decay, we know that the base needs to fall in between 0 and 1, so it's a positive decimal. And to find this base, we are going to subtract the rate from 1. Other information that we need to know, if we have an equation that looks like this, we need to know the different parts. So the A represents the initial value. The B is the growth or decay rate. And then in our fraction, in our rational here, we have a T, which is the elapsed time. And finally the H, which is, it's going to be the time frame given. Let's put time period given in problem. So if it says something doubles every 6 months, the H will be 6. And everything would be done in months. Okay, in a national park, a wolf population increases by 7.8%. So we're going to be working with that per year over a 10-year period. Okay, beginning in 1997. The formula P equals 124 times 1.078 to the power n modeled the wolf population P after n years. What was the wolf population in 1997? Okay, so we're seeing that the study began in 1997 and it's asking us about 1997, so that's year 0. And if we plug, you don't have to do this part, but if you plug 0 into your exponent, we know anything to the power 0 is 1. So we end up with 124 times 1, which is 124. So year 0 is the initial amount. Okay, and then B, what was the wolf population in 2007? So first thing we need to do is figure out how many years have passed since the study started, and that is 10 years. So we're going to use that as our n here. So we have 124 initial value. It's a growth rate of 7.8%, and we're doing to the power 10. So we end up with 124 times 2.12 to give us 262.8. Now we can't have 0.8 of a wolf, so your therefore statement would be, therefore there were 262 wolves in 2007. Okay, so when you're talking about physical beings, you can't have a decimal of a human, of an animal, so you round down. The number of giraffes in Shelburne is decreasing at a rate of 5.3% every 6 months. Okay, so we know the rate, but this is telling us every 6 months. So because it's not in years, we're going to be using a rational as our exponent. In 2003, the year which the study was conducted, there were 273 giraffes in Shelburne. Write an equation to model the giraffe population. Okay, so we're going to use P for population and N for, um, actually let's change that to T for time. And we get, so our initial population of giraffes when the study started. Now we have a decrease rate here. It's exponential decay, so we're going to be subtracting 0.053 from 1, and we get 0.947. So that will be our decimal. And as I said, because it's every 6 months, we're going to have a fraction over 6, and we don't know the time that will be passing. B is how many giraffes will there be after 30 months. Okay, so this is going to represent our T. Oops. Okay, so we can plug it in. Our T is 30, 273, 0.947 to the power 30 over 6, which is just 5, but I'm going to skip that step. So we're doing 0.947 to the power 5, and that's going to give us 0.7616. Multiply that by 273, and we figure out there are 207 giraffes. I'm pretty sure it's 207.8 or 0.9, but again, we can't have a partial giraffe, so you round down. How many giraffes will there be in 2010? Okay, so we need to figure out when this started, which was 2003. So 2010 minus 2003 is 7 years, but again, remember that our exponent is in months. 7 years times 12 is 84 months. So this is what we'll be using. Okay, so now we have 84 months. 273, 0.947. Now our exponent is 84 over 6. Again, that divides nicely into 14. So your exponent will just be 14, but I'm not going to write that step here. 0.947 to the power 14 is, sorry, let's get my calculator. Okay, 0.947 to the power 14, 0.4666, 0.467 we'll say, and that will give us 127 giraffes. Okay, now for the one where I'm going to give you options. When will there be 100 giraffes? Now it's giving us the population and it wants the time. Okay, so there are two ways to do this. There's trial and error, and there's logarithms. So we're going to split right down the middle here. We'll do trial and error. We'll do logarithms. So trial and error, you're going to write your equation, knowing that we're looking for 100 giraffes. And we need to figure out how many months it takes to get to 100 giraffes. So looking above, we can see that 84 months got it down to 127. So we know it's going to be something larger than 84 months. So if we try not 14 years, but let's say 16 years, So 0.947 times 16, oh sorry, 0.947 to the power 16 times 273, we get 114, so we're getting close. So when I tried t equals 16 years, which is 192, whoa, sorry, I shouldn't have done 16 years. 6 years, because it's divided by 6. My apologies. So 6 times 12, 72. Okay, so when I did, oh, I'm struggling here. 96 over 6, we got an answer of 112. Okay, so that didn't work. Let's try 112 over 6. Okay, so a decimal of 18.67. So we 947 to the power 18.67 times 273. We get 98.7. Okay, it's a little bit too much for our t. So we'll try one more at 111 over 6. So we do 0.947 to the power 111 divided by 6, which is 18.5, times 273 is 99.7. So 111, right around there, roughly 111 works. Now, this is trial and error. We were able to see above that t had to be greater than 84, and that gave us a starting point. You're not always going to be given that information, so trial and error can take a long time to do. The other way we're going to look at is called logarithms. Okay, and you're going to need to know what logarithms are going into grade 12 math. They get a little more difficult in grade 12, but I'm going to show you the basics, and that's going to help us determine an exponent, so a time that we're looking for in this case. So we have 100 equals 273 times 0.947 to the power t over 6. So the first thing we want to do is get rid of the 273. So we're going to divide both sides by 273. Okay, and that gives us 0.366 equals 0.947 to the power t over 6. Okay, this is good. Now we have one singular number on the left of the equal sign, one singular base with the exponent on the right. So to do logarithms, we're looking for our exponent. You're going to do the log of 0.366 divided by the log of 0.947. If you're on your iPhone, the log is the button that says log 10 when your iPhone is sideways. If you're on a calculator, it probably just says log. Okay, so if you do the log of 0.366, we get negative 0.4362. and the log of 0.947, we get negative 0.0237. And when you divide those out, you get t over 6 equals 18.44. And then to isolate t, we're just simply going to multiply both sides by 6. And t equals 110.7, which is roughly 111. Okay, so they get roughly the same answers. One trial and error takes a long time to do. Logarithms, you don't have to write all these steps down. You just know you're doing the log of the constant number, so the number that's by itself, divided by the log of the base. Okay, moving on. A new car costs $24,000. It loses 18% of its value each year after it's purchased. This is called depreciation. Determine the value of the car after 31 months. Okay, first thing we need to do here, so it depreciates every year, but this is giving us months. So we're going to turn our, the value of a car for time. So initial value, we're going to turn our exponent into a fraction. Okay, it's losing 18%, so 1 minus 0.18 is 0.82, and we're doing 31 over 12 because 12 months is the same as 1 year. You can do this, or you can figure out how many years is in 31 months. It's 2 point something, so you're getting decimals that way. Okay, so we do our 24,000. 0.82 to the power 31 over 12 is 0.599. And the car will be worth $14,373.54. Okay, and then last, the savings account has an annual interest rate of 5%. If you have $1,250 in your account, how much will you have in 5 years? So this is increasing. It's exponential growth. Money for time. Okay, we're investing $1,250, increasing at 5%, so 1 plus 0.05, and it's for 5 years. So 1,250, 1.05 to the power of 5 is 1.276, and they will have $1,595.35. Okay, thank you.